Today's nuclear medicine snack is quite a controversial one, but I like to talk about this because I have so many questions still unanswered and I also see so much potential. So please, most of this is probably my opinion, and I would like you to engage with me in the comments down below and give your opinions as well on this technology. So we are talking about using alpha emitters, specifically actinium-225, in therapy for patients. And here, just to demonstrate you the amazing results that has been shown or demonstrated in the clinic in patients with actinium PSMA. For me, the proof is always in the pudding, and in this case, the pudding looks nice. But I am a scientist and I have to ask some questions and try to understand, and that is my outlook. So we have an in vivo generator principle going on here because short-lived radionuclides like bismuth 213 can be difficult to work with. If you inject bismuth 213, you only have a 45-minute half-life, and that limits the potential of this radionuclide. So to overcome this limitation, they developed in vivo generators where they would inject the parent isotope, actinium-225, and in the patient it gives rise to the daughter radionuclide. So it's an in vivo generator. So actinium has a decay chain where it gives off 1 alpha, 2 alpha, 3 alphas, and finally 4 alphas while it is in the body of the patient. So it is not only generating bismuth 213, but there is 4 alpha emitters in this decay chain. This is quite a bunch. So why is there some issues involved with this, and why should we be careful? First of all, the daughters have different chemical properties, and you can see they are all over the place. So one cannot assume that if actinium-225 is bound to the chelator quite strongly, bismuth and francium and palladium will still be bound to the chelator because they have different chemical properties. So your actinium has a half-life of 10 days, but during these 10 days it changes to bismuth and palladium and francium. Although with a 10-day half-life, the first decay, I understand that, it still changes and the consequent daughter isotopes will not be in the vector anymore. Then there is the recoil effect. So when actinium-225 decays, because it's an alpha emitter, this is a high energy reaction and the resulting daughter isotope will be moved in the other direction according to Newton's principles and therefore be kicked out of the vector in essence. This is not demonstrated very clearly, but it is a theoretical concept that you have to take into account. It is like firing a shotgun and you get the recoil effect back, you will be kicked back a bit, and maybe this will kick you out of your chelator. Radiolysis is another important thing because we are dealing with high energy. We have to know if the molecules are still intact when there is all of these high energy decay reactions happening all around them. This needs to have some further attention. There is unfortunately also a lack of a stable isotope, so we could never really validate the radiochemical purity methods with a stable isotope. HPLC is hideously difficult to perform, and there is also some work to be done on this part of the molecule. Like I said, emission characteristic is not at all suitable for HPLC, although you will have other methods where you can measure other characteristics with HPLC, but it doesn't give off any useful gamma rays for HPLC. So currently radiochemical purity is done by a method where you spot your product at the origin and then you let it incubate and develop, and then you cut the strip into two pieces. You have to wait 45 minutes for the equilibrium to reach, because you want to measure the actinium through francium. So you need to know that the francium in the system comes from actinium that is at that point in the strip, and it's not old francium that just went through the system through the solvent front. This is a very tricky thing to discuss, so if you want me to make a video on the quality control of actinium, you can ask down below in the comments. This could take some time to explain, but it is a tricky system that I myself had to spend lots of time before I felt comfortable understanding it. So we do some assumptions during the QC. We measure francium 225, and we know that this is coming from the actinium peptide that is in the most top region, and then the bottom region, and then also we measure francium at the top that we believe is originating from the unlabeled actinium, and then we do a calculation to see the percentage of radiochemical purity. To give it the best chance to work, actinium, we need a very quick tumor accumulation and internalization, so that when recoil happens or when instability happens, the radiopharmaceutical is already at the tumor target. So the idea is you get a radiopharmaceutical with a very quick pharmacokinetics, very quick accumulation in the tumor, and internalization, such as what is present with prostate-specific membrane antigen. And then you don't need to worry about all of the instabilities, because it's already in the tumor and it stays there for the next 10 days. This is still a work in progress theory, but that is how we give it the best chance to work in the clinic. We cannot argue with these results. Whether the mechanism is the actinium PSMA or some other mechanism of action, we have seen amazing clinical results, and I've had the pleasure to see these patients in real life, and their life quality has substantially increased. So please do not get me wrong. I would love actinium to work for all cancers, but I think we should stop and think about this scientifically also. If you have any comments, which I'm sure some of you do, maybe counter arguments or anything that I've missed, you can comment down below. If there is any parts of this presentation you want me to give you some more information on, also comment down below, and other suggestions of chemistry, radioactivity, anything you want, you can comment. I want to thank BioRender for the use of their program during this presentation.